So thanks for coming. So we have Nicola Lorenz from University of Hamburg. Actually, what I forgot the title. Span set of vertices, right? No one is. Yeah, please.
Okay, yes, so I'm going to start with my talk, and my goal of the talk is that in the end of my talk you have a nice understanding of normal spanning trees. So I already wrote some nice theorems about normal spanning trees on the blackboard, but I think you still need some definitions to understand these theorems. So please forget about the theorems for a moment, and I would like to start with a definition. Okay, so first I would like to define what a normal spanning tree is. And it might be the case that you already know normal spanning trees, but not under the name normal spanning trees, but under depth first search trees. But for my convenience, I'm going to stay with this name. So a normal spanning tree. T of G is a rooted tree such that, so first of all we want that the tree is spanning, so that all the vertices of G are contained in our tree. And second, we want that our tree is normal. So remember that when we have a root, the root induces a partial order on our vertices, and I want that all edges that are not contained in our tree but in our graph G, that the end vertices are comparable in our tree order. Okay, and this we call the normality. So let me draw a picture, and in my world the trees grow upwards, so I'm going to stay with my notation. So we have this tree, we have a root, and we want that whenever we have an edge outside of the tree, it should lay between two comparable vertices, so like this. So in other words, when we consider this vertex and we follow the path on the tree to the root, then the other end vertex of my edge should lie on this path. So what we don't want is an edge that lies between two incomparable vertices. So this we don't want to have. Okay, next I would like to define what a normal tree is. So the definition is not too different.
Is every normal spanning tree also dispersed tree, or?
So as far as I know, yes. We can. No, sorry. What was the question?
So every DFS search tree is a normal spanning
yes,
tree, right?
exactly.
But is converse true?
No, I don't think so.
Okay.
Okay. So I'm going to define a normal tree. Okay, so normal tree is also a rooted tree of G, such that, and we don't want to have this spanning part, but we also want a condition that shows that is like showing the normality, and what we want to have is that the end vertices of every t-path are comparable in our tree order. So what is the t-path? With t-path, I mean that the end vertices lie in our tree, but the inner vertices don't. So the picture looks quite the same. So whenever I have a t-path, I want that the end vertices are comparable on t, and what I don't want is paths that look like this, so that the end vertices are not comparable in our tree log. Okay.
So the tree is oriented in a way, so the t-path cannot go up and down.
Yes, so I want that all inner vertices are outside of the tree.
Yeah, but when you say t-path, do you allow paths like going down? You don't allow, right? You don't allow.
Do you mean something like this?
Yeah.
So this is not a t-path because then one inner vertex lies in my tree. So I only mean when the vertices are outside of the tree.
Oh, so the t-path. Okay, so it's not a path on the tree. It's path whose ends are on the tree, right?
Yes, exactly. So.
Okay.
All right. So if there are more questions, please let me know. Okay, then I'm going to continue. And so probably you already know that every graph has a normal spanning tree because you maybe already know the algorithm that is depth first search. I would like to show you another algorithm and also what I didn't told you so far. So I'm from the University of Hamburg, so of course all my graphs are infinite. And so I would like you to not only get familiar with normal spanning trees now, but I would also like to show you your first proof about an infinite graph. So let's consider the following theorem. That is that every countable graph has a normal spanning tree. Okay.
She has some connectedness.
Yes, sorry. So I didn't say this. So in my world, every graph is connected. And whenever I write U, then this is a set of vertices of G. Okay, so whenever I forget to say that G is connected, yes, then I mean if G is not connected, what we can do is we can go for every component and there we can find a normal spanning tree. But for like a normal spanning tree for the whole graph, of course, we need that the graph is always connected. Okay. So our countable graph is also connected. And how do we prove this? Okay, so the first thing that we do is that we enumerate our vertices. And now my idea is to go step by step and construct normal trees such that in the end they will span the whole graph. Okay? So construct an increasing sequence of normal trees such that they all have the same root and that they extend each other. So these are all normal trees. And I also want that these trees contain the first n+1 vertices. Okay. And now what we can then do is then we can just take the union of all of these. So suppose we already have constructed these normal trees, then if we take the union of these, then T will be our desired normal spanning tree. Okay? So this will still be a tree. It will also be normal, because if we have a forbidden edge, then there must have been any normal tree where this forbidden edge was already. But this can be true because they were all normal. And T also spans the tree because we add our vertices step by step. Okay? So now I only have to explain you how I construct these normal trees. So we start and just take our first vertex and our enumeration, and this is just our first tree, T0. And this of course is a normal tree. And now we continue and construct T1 and T2 and so on. And let's say we already have constructed our tree Tn. And Tn also has our conditions, so it's a normal tree that contains all our vertices. And now we want to define Tn plus 1. Okay. And now it might already be the case that Vn plus 1 is already in my tree. But then this would be great, because then we could just say, okay, then Tn plus 1 is just Tn. So suppose Vn plus 1 is not contained in our tree Tn, then it lies somewhere outside in a component of G minus Tn. And now what we do is, now we consider the neighborhood of this component that lies in this tree. So maybe it looks like this. Okay, so this is the neighborhood of my component C. And now the first thing that we observe is that actually this can't happen. So what I have here are two neighbors that are incomparable in my tree order of Tn, but this can't be true. Why is this the case? So if we have something like this, we can just follow this edge, find a path in my component, and follow this edge. And then we have found a forbidden t-path, because the end vertices lie on incomparable vertices in my tree, but the inner vertices are outside of my tree. So instead, let me draw this picture correct. So we have the case that all my neighbors of the component are comparable, so they form a chain in my tree. Okay, and now the next thing I do is I take the maximal element of this chain, which is in my example this one. And now what I do is I know this is a neighbor, so I can walk into this component, and now I can find a path in my component to my favorite vertex that I want to add. Let me call this path here P, so this is P. And now what I do is I simply add this path to my normal tree Tn, and this defines me Tn plus 1. So why is this a normal tree with all the conditions I need? So first of all, clearly Vn plus 1 is contained. It's still a tree, and also it's normal. Why is it normal? So suppose my Tn plus 1 is not normal. That means that I have a forbidden t-path, but this forbidden t-path can be contained only in Tn, because this was normal, and it can also not have the end vertices in my, not both end vertices on my path, because clearly every path is also normal. So, in other words, my forbidden path must look like this. Okay, so it starts on P and it ends on Tn, and also it must end it must end here, because the neighborhood here was comparable to the other vertices. But now we can see that then we would have chosen this vertex here as our maximal element, but we took this one. So our path looks like this, but this is allowed, so this is not a forbidden t-path. So indeed, Tn plus 1 again is a normal tree with my the conditions I need. And this is the construction of my Tn's. And then the union of all of these Gn is my desired normal spanning tree. Okay, so this was our first proof. So, any questions? So I would like to give you 2 observations. So the first thing that we can see is if we have a set of vertices in our graph that is countable.
Well, maybe I have a question.
Yeah.
So we didn't know an answer to Simon's question earlier, but in some sense what you're doing here is also somehow depth first search. Just
okay.
with some ordering of the vertices and then you look for these in order somehow. Is this a way to construct all normal trees? So just fix an order of the vertices and do this kind of sequence?
So I think not. So this is just one algorithm how to find them.
Okay.
But I suppose there's more ways to. So I think there will be more normal spanning trees on some graphs that look different. I think. And maybe also, yeah, okay, that's not really an answer. But I think we could, yeah, just look at one example graph and we could find different normal spanning trees, and one of them might be also an observation. So let me start with the second one, because when I did this proof, I was completely free which vertex I start with. So I can just choose any vertex as a root. So clearly when I start with V1, then the normal spanning tree might look very different. So does this answer your question somehow?
In some sense, yes.
Yeah. Okay, so we can construct T with any root. Okay, and the other observation is, so let's say we have any infinite graph and we have a set of vertices U that is countable, and now I can do exactly the same proof, but instead of enumerating my vertices of G, I enumerate my set U, and then I can find with the exact same algorithm a normal tree that contains my vertex set U. Okay. And even I can find this normal tree such that they contain U cofinally, which means that for every vertex in my tree, there's always a vertex from U that lies above it. So, and this is exactly how I constructed them. So there's always a vertex from our vertex set U that lies above it or at the same height. Okay. So these are 2 observations that we will not look too much at for now at the moment, but they will be a bit more interesting later.
I don't actually understand the meaning of cofinally.
Okay,
so for instance, what if you have a star? Like, then what do you mean by having something above?
So you mean something like a normal tree like this?
Yeah, and then.
To be that U is cofinally, we need that also every leaf is also contained in U. So cofinally means that for like any vertex in my tree, there's for all B there always exists a vertex in my set such that this one lies above my vertex.
Yeah, so for instance, can I have if the graph is like one vertex versus infinitely many other vertices?
Yes, so like this.
Yeah, and then
so,
to start with.
So if we want to have cofinal vertex set in here, then we must at least have all the leaves in U, because otherwise I could, so if I have something like this, and now I choose this as my vertex V, then I don't find a vertex from U that lies above it or at the same height.
Oh, I see. So U is not every vertex. U is like
Yes, U is a set of vertices.
some set of vertices. I
Yes.
see.
But this is not equivalent to saying just all the leaves have to be in U, right? Because you could have some infinite path.
Exactly.
Okay.
So it might be the case that we have an array in our tree, and then we have no maximal element that we can where we can just say, okay, this is like my highest view. Okay. So next, I would like to continue with a question. So let's suppose that our graph is an uncountable clique. So now we just considered like a countable graph. So let's suppose our graph is uncountable and it is an uncountable clique. Let's say this one. Does this graph have a normal spanning tree? Okay, and now you might think about this for a moment, and the answer of this question is no. So, why not? Okay, so suppose we have a normal spanning tree that contains the uncountable clique, then it must be an infinite path. I call them ray. Because otherwise, if we have any branch that looks like this, we get forbidden edges that we don't want. So our normal spanning tree has to look like a ray, but the problem is that a ray is countable, so they only fit countable many vertices inside. So our uncountable clique is too large to fit inside.
When you have two branches, how do you argue that there's a shortcut between
Here's the clique.
Yes.
Okay, right. Very good.
Okay, so but this I think sounds a bit odd because I just showed you an algorithm such that we can find for like a very big graph a normal spanning tree, and now the uncountable clique doesn't have a normal spanning tree anymore. So why does this proof doesn't work anymore for our uncountable clique? And the problem is that when I choose this maximal element, it's not clear that this one exists. Because it might happen that, as we saw here, that our tree can contain an array, and then we might have a component here that has a lot of neighbors here, and we never know what the maximal element is. So this is the problem.
This is not a problem in the countable case?
In the countable case, it's not a problem because so this tree might be so it is very big, so it's infinite. But when I do my construction here, what actually happens is that every of these trees is always finite. So I can never have a ray in my tree. Okay. Okay, so now let's consider our theorems here. So now I think we are ready to get a bit more into it. So now these are like two easy theorems, but I would like to show you that there's also uncountable graphs that still have a normal spanning tree. So this is why we are going to consider the following theorems. So let's start with theorem 1. And this is a theorem from Jung. So a connected graph G has a normal spanning tree if and only if G is a countable union of dispersed sets. Okay, so let me define what a dispersed set is. dispersed if for every ray in our graph there exists a finite separator that separates my set U and R. Okay, so let me draw a picture for that. So we have an infinite path. This is a ray in our graph. And we have our set U. This doesn't have to be connected. And now we want to find, so for every ray, we want to find finite separator separating my ray and my set of vertices U. Okay. And now I would like to give you the idea of how this proof works. So I'm going to start with the forward implication. So, what we do is, so we have a normal spanning tree. And now the idea is, so now we want to find our countable union of dispersed set. And the idea is that we just go level by level. So we start with the root, and this will be our U0. And then we continue. So then we look at the neighbours in the tree of our root. This is U1 and so on. And these are countably many. And together they span my whole graph. And now it just remains to show why every of these UN is dispersed. But I would like to skip the proof of that. But this is the idea. And for the other direction, I want to again construct a normal spanning tree. So let's suppose that our graph is a countable union of dispersed sets. And now also the reason why I showed you this proof before is that you will notice that the idea of how we find normal spanning trees will not be too different. Okay, so first of all, when we look on the left side, what we did was we found an enumeration of the vertices of the graph. Instead, I will do something similar. So what I just consider is my dispersed sets, and these also span my graph. And this gives me some kind of an enumeration, so they don't have to be disjoint, but I kind of have like an order of my vertices, how I consider them. And now what I do is, again, I want to construct normal trees. So I want to find an increasing sequence of normal trees such that they extend each other and have the same root. I want them to be normal trees. And I also want that they contain my dispersed sets. So U0 until UN should be contained in Tn. And moreover, and this is what we kind of saw before, we also want that every Tn now is rayless. So now I already gave you the reason why. So by just making sure that every Tn is rayless, we will not get a problem like here. We can always find the maximal element. Okay, and then also as before, the same arguments, the union of all these Tn will give me my desired normal spanning tree. So what we now have to do is we have to like define our sequence of normal spanning trees, and instead of adding to Tn my whole dispersed set UN plus 1, I would like to do it step by step. So what I instead do is this is formally not correct to say it, but I would like to enumerate my un+1. Why is it not formally correct? So this dispersed set might be very huge. So instead, I'm going to find a word order on them. And in case you're like absolutely not familiar what we are doing right now, so our goal is that we now do a recursion, but it's transfinite. But if you have never seen something like this, just act like this is just a countable set, and then we will be quite similar. There will just happen one more thing, and that is that we will also have to deal with limits. I'm going to explain what we will do in this case. Okay, so all right. So now again we construct an a continuous increasing sequence of normal trees, and we start with our Tn from the sequence here, which was a normal arrayless tree that contains our dispersed sets. And now I will add step by step my vertices from my dispersed set un+1. So I'm going to call the next one Tn1 and so on. And I again want that these are normal trees. I want them to be rayless. And I want that they contain all smaller vertices. Okay. And then with this sequence, I then can define the next element of this sequence here, which is Tn+1. And I will just take the union. I will just take the union of these. And then this will be again a normal tree that contains my vertex sets un+1. And I also hope that it's going to be rayless again. So let me show you how I construct these normal trees. So suppose I'm going to use this picture again. So suppose that we have already constructed Tn beta, and now I want to construct Tn beta+1, and what I do is I consider my favorite vertex, and suppose it's not already in my tree, so it again lies outside. And as before, I want to find the maximal element of the neighborhood of this component that my vertex lies outside. And indeed, I find this one because my tree Tn beta is rayless. So I can do exactly the same as before, and I can just add to my tree here a path. Okay, so the idea of this proof is not different, and also I stay rayless because every time I just add a finite path. But this was also when we consider that we are a successor, but it might be the case that we are a limit, and what we do then is that we take the union of all smaller trees and this might cause a problem. So whenever I take the union of trees, which I do there, and also here, I must be sure that I don't construct a ray. So how could it happen that I construct a ray? It can happen that before I always added a finite path, like this. and so on. And then, of course, every tree before was rayless, but as soon as I take the union of these, they construct a ray. But what happened here, so since I'm considering un+1 at the moment, all my vertices here are in my dispersed set un+1. So I found a ray in my graph that can't be separated finitely from my dispersed set un+1. And this is a contradiction because of the definition of a dispersed set. So also, whenever we take the union, we stay rayless, and our construction still works. All right. Now I would like to talk about theorem number 2. And I'm not going to give you the proof because it's very similar to the one that I just showed you. It's just the local version of it. And as before, we can also do the same observation. So we can, instead of working with the whole graph here, we can just find, so I don't want to make this away, but instead of writing G, we can also write U here. So use the countable union of dispersed set, and then the whole proof works with the same ideas. And also in the other direction is very similar. Okay, so then I would like to continue with theorem number 3. Okay, and for theorem number 3, we need a new definition. So the theorem is that a connected graph has a normal spanning tree if and only if every minor of G has countable coloring number. So what is countable coloring number? So I say that a graph has countable coloring number. If there is a well order of the vertices of my graph with the following property. So I want that for every vertex in my graph, I want that the cardinality of the neighbours of my vertex that are smaller regarding to my well order, I want that this is finite. Okay? So let me draw a picture for this. So I have a well order of my vertices of G, and for every vertex that I pick, there's at most finitely many vertices in the neighborhood of V that are lying below my vertex. Okay. And
so why is it called the countable coloring number instead of finite coloring number? I don't know.
Exactly, good question. So let's continue. I would like to give you one observation.
Asking the right questions today.
Yeah, this is degeneracy, right? So,
Yeah, because you can't give a total upper bound. Every one is finite, but you have all the numbers.
But this is still more like degeneracy than color. You have a bi-clique that's infinite. It has it doesn't have this property.
The degeneracy plus 1 is sometimes referred to as the coloring number.
Yeah,
This is the coloring number for boundary
right, right. So the finite
Nothing
graph,
to do
people
with
call it
chromatic
coloring number.
I see.
like video room.
Okay, so yes, good question. So, what does a well order have to do with colorings? And the observation is that a graph with countable coloring number has at most countable chromatic number. And I was planning to say that I invite you to think about this for a moment, but I think you already did. So let me just explain how it works. So what we do is we want to find a coloring of the graph, and we can be very greedy. So maybe there's a very nice chromatic number that is very small, but we only want to show that it's most countable. So what we do, we go step by step and find a color for every vertex. So let's assume that we already have a coloring for an initial segment, and next we want to give V a color. And what we do is we just consider all the neighbors that already have a color. Let's say this has color 1, 2, and maybe 4. And then what we want to do is we want to give V just the smallest available color. So I would give it, in my example, a 3. And there always exists an available color because we have only finitely many neighbors that already have a color. So we can always find a color that is still available since we have infinitely many colors. Okay. All right. So so we plan to look at theorem 3. So I would like to show you the idea of the forward direction. So this proof follows from 2 facts. Fact number 1 is that the property of having normal spanning trees is close under taking connected minors. Okay, so whenever we have a normal spanning tree and now we consider a minor, then this also has a normal spanning tree. And to show this, we can, for example, use the characterization that we already know, which is this one. And instead of, so we know that our graph has a normal spanning tree, so it is a countable union of dispersed sets. And now what I want to do is I want to look at my dispersed sets, and I consider the corresponding sets in my minor, and then I can show that these are also dispersed sets. So our minor still has a normal spanning tree. Okay, so this is the idea, but I'm going to skip the details. And I'm going to continue with the second step that we need. And that is that every graph with a normal spanning tree. And this is a very nice observation, because here we see what normal spanning trees have to do with the countable coloring number. So they have countable coloring number. Okay. And why is this true? So suppose we have a normal spanning tree. And now I want to define a well order of my vertices. And what I do is I just go level by level. So I start with the root, and then I go on. And for every level, I find a well order. And what I then do is I concatenate the well orders. So it looks kind of like this. And then this defines me a well order of all the vertices of my graph. Now the question is why this well order satisfies that we have countable coloring number. So let's consider a vertex. And let's say this vertex lies here in my normal spanning tree. And now I want to consider the lower neighbors regarding to our well ordering. So let's first see how the set looks over here. So either there are some vertices in the well order on the same level, or the other vertices lie in the lower neighbor, in the levels below it. But since we are a normal spanning tree, so by normality, all the neighbors of V can only lie in its down closure, which is this set here. And a down closure is finite, so we can at most have finitely many neighbors in this set here. Okay, and this is the forward direction, or the idea at least. And now I would like to consider the backwards direction. Okay, and what do we do? So let me do this formally, but if you can't follow this, I will get back to you in a minute. So what we do is we do a transfinite induction on the cardinality of G. And first we notice that our statement is true if kappa is countable. So this is easy to see. And now we consider if kappa is uncountable. And also, let's assume that for all graphs that are smaller, for all G that are smaller, that our statement is true. Okay, so whenever we have a smaller graph, G prime, then we know that if this one has the property that every minor here, that every minor of G prime has countable coloring number, then this graph has a normal spanning tree. And now, in case you just ignored this, please come back to me. And now what we would like to do is we kind of want to use the same idea as before, so we kind of follow the same structure of the proof. So first we want to do something like enumerating the vertices, but instead what we do is, and this is like the whole magic of the proof, and I'm going to skip all the details because this is very complicated. But what we can do is we can find a continuous increasing sequence of subgraphs of G with a lot of properties. I'm going to tell them in a second. So we find an increasing sequence, and they all span our graph G. And then, as before, we want to construct an increasing and continuous increasing sequence of normal trees that contain these subgraphs, or better to say the vertices of these. And now we want to have some conditions. So first of all, we want that this is contained in here co-finally. And also, we want that these graphs are all not too small, so they are all infinite. They are not too big, so they are smaller than kappa. And they're induced and connected. So in other words, by our assumption, we can say that these all have a normal spanning tree. So they have a normal spanning tree. And moreover, I want them to have one more condition, and that is that for every Gi, when I consider the components, so this is a component G minus Gi, then I want for every component that the neighborhood of this graph, the neighborhood of this component is finite. And this property I call finite adhesion. So I want that every of this graph has finite adhesion, because then what I can do is, together with the property that these are contained in here co-finally, so this this means that our property of having finite adhesion adheres also to our normal trees. And I'm also going to skip all the details of here. So let's consider, and then as before, taking the union of all these trees gives us our desired normal spanning tree. So let me take the last minutes to explain you how we construct our normal trees this time. And so let's suppose that we have already constructed our tree Ti, and Ti contains the vertices of Gi co-finally and has all the other properties. And what I now want to do is I want to define Ti plus 1 such that it contains the remaining vertices of Gi plus 1 that are not already contained in this tree. So let's consider these vertices that are not contained. And now this is the first time where I don't only consider one vertex, but now I want to add a lot of vertex at the same time. And what I do for this, so first let's consider the neighborhood of these components, and they again build a chain. And by the fact that this tree Ti has finite adhesion, we know that this chain has a maximal element, and the same is true for this one here. And now what we do is we walk, so we take any edge here and walk into our component here, and we will fix this. We will fix this vertex. I'm going to call it R. And now what we do is, now we observe that, so I said before that our GIs are all having a normal spanning tree. So so our normal spanning trees are countable union of dispersed sets. So if I just take the intersection with any component, these are still a countable union of dispersed sets. So they still have a normal spanning tree. There's only one problem. So just having a normal spanning tree doesn't mean that that this tree is still normal in our graph G. But I'm going to also skip this detail, and let's just say that we can find a normal tree in this component with this root here, that contains my favorite vertices here co-finally. And I do the same here. And what I then do is I simply take again my old tree Ti, and now I add all my favorite edges here and all the normal trees here. And then this will be Ti plus 1. And now we can check all the conditions. And then again, this is the normal tree that has all my conditions I need. The only thing that I have to talk about is what if I actually consider a limit. And whenever we have a limit, then I also simply take the union of all smaller Ti's. And also you can show that also this is a normal tree with all the conditions I need. Here I just have to say that this was a continuous increasing sequence, so also G lambda is just the sequence, the union of all smaller GIs. And yeah, then this gives me the construction which works. And yes, so then we have constructed our normal spanning tree. Last but not least, there's also a local version of it, which I have written here. So U is contained in normal tree of G if and only if every minor of G supported by U has countable coloring number. Yes?
So, sorry, where did you use the hypothesis that every minor has a...
So when I said that these GI are all smaller than kappa for infinite and used subgraphs, every GI is like such a candidate. So the statement is true, and then I can find a normal spanning tree. So and here you're right. There's a lot of details missing. So so what I say. So you never actually saw the part where I use countable coloring number. That's true, because here, so this is the part, so constructing these is like the biggest black box in my talk, because yeah, I was skipping this. So having a countable coloring number gives you some, so you can exclude some minors, which help you to construct these GIs with all the properties we need. Okay, yeah, so that's also a local version. And here maybe I can just say that a minor supported by U just means that in every branch set of my minor there's a vertex of U. And yes, so here the ideas of the proof, so there are some that you can adapt, so it's some of them work the same, and for some there also you need to work more. But yes, that's all I was planning to tell you in my talk. Yes.
Thank you. Questions? Yes.
Yes. Is it true that if my graph is just some ray, that it is its vertex set is still like a countable union of dispersed sets?
Yes.
So what is a normal spanning tree of a ray? How does this look? What does this look like?
For example, just the ray.
Ah,
That's not a lot of tracks.
so the because it seemed to me that in your proof you show that every time you increased your normal spanning tree, you don't have a ray.
Yeah.
But then in the end it's okay that there is a ray.
Yes, so if you take the union, it might contain a ray.
Okay. Finite infinite
But if
thickness.
you
yeah. Okay.
So yeah, so if we have an array, this can be just the normal spanning tree, or you can also choose another vertex. For example, you can also do this.
Yeah.
There's some options. Yes.
Is there some open problem you could state in this area?
Yes. I was thinking that someone would ask this, but for the questions that I have in mind, you actually have to understand the big black box here, because what we define here is also like a generalization of the normal spanning trees, which we call normal partition trees, and every graph, also like the uncountable graph, has a normal partition tree, and then you can like ask more questions in this direction. So I would say maybe I'm not going to write anything in this direction on the blackboard, but we can of course talk about this later.
We did not talk about theorem 4, correct?
Sorry?
What is a minor supported by you?
Ah yeah, so if we have a minor, maybe looks like this, then for every branch set I want that there always lies at least one vertex of my set of vertices inside the branch set.
Is this for you different from being rooted at you?
What do you mean with that?
What you just gave is what you just gave is yeah.
But you
Ah,
have
so
like 2 vertices of U inside one block.
Yeah, but it's usually okay for if you don't, if you just say rooted at the set, then this is exactly the definition.
Oh, okay, then
I was just curious if there was a reason, because maybe something strange happens when you go infinite.
Then the reason was that I had a hole in my knowledge.
Okay.
Do you know other results in infinite graph theory that talk about these supported minors?
Oh, so yes, when I was coming up with this definition, I saw one paper that also used this notation, but I don't remember which one.
Okay.
Right, any other questions? So if not, let's thank the speaker.